Hi, this is another tutorial in my series on the conservation of mechanical energy. And what I'm going to show you in this particular tutorial is how we can apply the conservation of mechanical energy to a problem where we've got a smooth plane which is inclined at 30 degrees to the horizontal. We have a particle here of mass 4 kilograms which is released from rest and slides down the plane in the line of greatest slope. And what we've got to do is find the distance that it's travelled when it reaches a speed of 8 meters per second. And you can solve a problem like this in three ways. You can solve it by the conservation of mechanical energy, or you can solve it by the work energy principle, or you can solve it by good old-fashioned Suvat equations, the equations for constant acceleration. Now what I'm going to show you is all three methods, but I think you'll find at the end of the tutorial the method here where we look at using the conservation of mechanical energy is the best one for such a problem. Okay, well let's just start then with using the conservation of mechanical energy. So when no external forces other than gravity do work on a particle during its motion, the sum of the particle's kinetic energy and potential energies remains constant. So to do a problem like this, we take two levels. We'll take the starting level, we'll call it A, and where the particle finishes here, we'll call it B. And we need a zero level of potential energy. We'll have that zero level on the base here. So when we look at the conservation of mechanical energy, we look at these two positions. We look at the sum of the gravitational potential energy at A, and we add it to the kinetic energy at A. And because this is going to be a constant value, it's going to be exactly the same as the sum of the gravitational potential energy at B plus the kinetic energy at B. So, what is the gravitational potential energy at A? Well, it's mgh relative to our zero level. And the h will be this distance up through here. Now in the past we've worked out h for inclined planes. We just use trigonometry. We say that the sine of 30 degrees equals the opposite side over the hypotenuse. Well, the opposite is h and the hypotenuse is our distance here of d meters. And if we multiply both sides by d, we end up with h equaling d sine 30 degrees. So, for the gravitational potential energy at A, we've just got mgh, 4 for the mass, g and h. So that's going to be times d sine 30 degrees. Now as for the kinetic energy at A, half mv squared, well because v is going to be 0, that term for kinetic energy is going to be 0. No kinetic energy at A. So it equals now the gravitational potential energy at B. But at B, the particle has no height above this 0 level, so there'll be no gravitational potential energy at B. But what about the kinetic energy? Because it's moving, then we've got the kinetic energy as a half times mv squared, m being 4, so we'll say times 4, times v squared. V is 8, so that's going to be 8 squared. Well, 4 times g at 9.8 times the sine of 30 comes out to be 19.6, so we've got 19.6 times d equals half of 4 times 8 squared, which is 128. So if you divide both sides then by 19.6, you get 128 over 19.6. Work that out in your calculator and it comes to 6.5306 and so on. Round that say to two significant figures and that's 6.5 meters to 2SF. So we've got d equals 6.5 meters then. Well, that's one way of doing the problem, but as I say, it's not the only way. We could use the work energy principle. I'll run through that for you now. Now, for the work energy principle, we've got that the change in the total energy of a particle is equal to the work done on the particle. So first of all, to get the change in the total energy of the particle, we need to look at the energy changes that take place going from A to B. Well, first of all, there's going to be a change in kinetic energy. It gains kinetic energy going from A to B. So we'll look at that first. The gain in kinetic energy, Ke. Well, what's it going to be? Well, at B, it's going to have kinetic energy of a half mv squared. That's going to be a half multiplied by the mass, m, multiplied by v, which is 8, squared, half mv squared. And then we've got to subtract the initial kinetic energy, which would be a half mv squared, half times 4 times 0 squared. And if you work that out, what you get is 128. So that's 128 joules. Now, there's also been a change in potential energy. As we go from A to B, it loses potential energy. So we've got to look at the loss in gravitational potential energy. So, at the start here, relative to this 0 level, it's going to be mgh. So that's going to be m at 4 times g, that's 9.8, times h. And h we've seen is d sine 30 degrees. So if we work this out, we end up with 19.6 multiplied by d, and the units will be joules. So according to the work energy principle, we've got that the change in the total energy, let's just write change in energy, is equal to the work done on the particle. Well, any work done on this particle would be work done against resistance. Let's just write that in here, work done against resistance. The question is though, what is the resistance? Well, this is a smooth plane. There's no friction acting on our particle. So the work done against resistance will be 0 in a case like this. However, if the plane were rough, which will be in my next tutorial, then there will be some work done against resistance. So we know that the work done against resistance is going to come to 0. So what's the change in energy? Well, that's the gain in kinetic energy, 128 joules, minus the loss in gravitational potential energy, which is 19.6 times d. So if we just add 19.6 d to both sides, we end up with 128 then equals 19.6 d, and if we divide both sides by 19.6, d turns out to be 6.5306 again, what we had before. So if we round this up to say two significant figures, d turns out to be 6.5 meters to 2SF, as before. So you've got this method then, the work energy principle. Now, as I say, there is another method, and that is the Suvat equations, the equations for constant acceleration. And I'll run through that so you can see how you could have done it that way. Now, when it comes to using the constant acceleration equations for this problem, we need the acceleration, and we haven't got it. So let's just mark it in on this diagram first of all as an acceleration downwards of a meters per second. And to get that, we need to put some forces on this diagram so that we can use Newton's second law of motion, force equals mass times acceleration. So we need to put on, say, the weight, acting downwards, mg, 4g in this case, newtons. We'll have the normal contact force from the surface. We'll say that's r newtons. There's no friction, so there's no other forces involved. It'll also be a good idea to put a dotted line in here and mark in the angle in here as 30 degrees, same as the plane. So the first thing that we need to do is get this acceleration by considering Newton's second law by resolving downwards in the direction of motion. So resolving downwards, we end up with our force down the plane is the component of the weight 4g sine 30 degrees. That's the only force acting down the plane, and that's going to be equal to the mass 4 times the acceleration a. And if we divide both sides by 4, you end up with a equaling g sine 30, which turns out to be 4.9 meters per second. Okay, so then all we need to do is set up our suvat, S for displacement, U for initial velocity, V for final velocity, A for acceleration, and T for time. So what are these values going to be? Well, if we take the direction of motion as being positive, that's down the plane, then the displacement S is going to be the d meters, what we're trying to find. U will be 0 meters per second. V, the final velocity, was 8 meters per second. The acceleration, 4.9 meters per second. Time, well, we're not interested in that, we don't want it, so we'll just leave that. So we're looking for an equation then that doesn't involve time. That's got to be v squared equals u squared plus 2as. So that means if we substitute these values in, we've got 8 squared equals u squared, so that's 0 squared, plus 2 times a at 4.9 times s, which is d. So we've got 8 squared, which is 64. We've got 2 times 4.9d, that's 9.8d. And if we divide both sides by 9.8, we've got 64 over 9.8. And believe it or not, that obviously comes to what we had before, 6.5306 and so on. Okay, which when rounded gives us that therefore d equals 6.5 meters back again to two significant figures. Okay, so we've got 3 methods then that we've looked at, and I would suggest that the first method, using the conservation of mechanical energy for this type of problem, was the easiest one to work with. But I'll leave it up to you to obviously decide. Well, that brings us to the end of this particular tutorial, and as I say, in the next one what I'm going to do is look at particles sliding down a plane, but only this time it's going to be rough. And I'm going to show you again how we can use the different methods, and I hope you'll have a look at that and see how to do such problems. Okay,